Okay, so I'm going to cut the crap. My name is Majid, so I'm going to start. So we are talking about contact and complementarity, right? That's exactly what we are talking about here. And we want to plan through contact. So the first question is that, so you is saying, so we plan forward, we don't use gradient. This is at least the baseline. But MO is still in favor of gradient. And, the first question is that people who were thinking about gradient now are moving toward either sampling or, just sorting, the way it was. So what do you think about that? So should we go with the gradient, with sampling, with CIO, with the
like I said, something is plan B. It will work if you wait long enough. Actually, I mean, if you go back further in time, there is a thing called simulated annealing. You can prove that it will find the global minimum of any function with probability 1, as long as you wait long enough. So yeah, that's always there.
Mm-hmm.
Whatever software you're using, you should have that in the background if all else fails. But there's no reason not to use faster and more accurate methods if they have to work.
But you know that when you have complementarity, we lose the gradient-based conditions that we have normally, like constraint qualification and so on.
So first of all, we can if you even that's two answers. One, that's precisely why I don't do complementarity in Java. I invent the new physics model, which is analytically differentiable smooth. But even if you get complementarity, if you solve the complementarity and found the minimum, you can compute derivatives at the minimum under the assumption that you are at the minimum. So you can do it. It's just that the gradient would probably have to follow more zigzaggy paths, and then you optimize it myself.
What do you say?
I mean, look, MO is in favor of doing the right thing, and that's commendable. And is indeed very useful. In Joko, you did a lot of things right, and we're very happy about that. On the other hand, Taylor wrote MJPC in 3 months. Well, how long have you been working on optical? 5 years?
Well, no, it's hard to tell because now I work on the beach, which is work. It's I achieved work-life balance like the European way.
So
there's no comparison because what I'm doing is I'm designing a language for optimization. So imagine designing MATLAB for the first time. So I can tell you that the framework is at the 3rd rewrite and redesign right now. So just in terms of time, okay, so the 3rd redesign and rewrite from scratch of the whole framework took 8 months this time. Adding MPC sampling to it took about a week, and the only reason it took so long is because I have a much more elaborate sampler that does 20 different things. Importing all the MJTC models and cost functions took 12. So basically, the thing that you call optimizers or solvers, whatever, that is surprisingly simple compared to designing a new language and implementing it and getting it to work. Maybe I'm not good at it, I don't know, but yeah, So for example, this trajectory optimizer based on gradients, this Acrobat and Hopper that I showed you, those are from 2018. I haven't released them, doesn't mean it's wrong.
Oh, but the question is that does it work in the real world? CIO is great, and Ensemble CIO, you showed that it works in the real world, but nobody could replicate that.
That's why. So I'm going to replicate it for you, and then you don't need to know. You just click around.
So basically, nobody knows. You know the magic, and we follow that.
No. So it took me a while to understand.
Yeah, exactly. But we want to understand it,
Yeah. So when the version that I'm implementing is a lot simpler, when you read the documentation, it will be completely obvious. Like I said, it's a new type of actuator with a new type of cost. I can write down exactly what they are. So it's Mujoko physics, a new actuator added to it, generic optimizer on top of it. You just need to understand what that actuator is. And it's basically the actuator says, okay, I'm going to create a contact that doesn't exist. I'm going to put a contact frame somewhere, and I'm going to specify what contact forces I want in that frame. That's basically what it is. And then there's a very specific cost, which is really the magic trick. It says, okay, if you did that, that's fine. But now, since that contact doesn't exist, these two bodies should really get close to them. So it's almost a complementarity cost between the magic force that you invented and the distance that should go to 0. So
heuristically, you try to basically close the gap.
Yeah, exactly. So the idea is you understand that you want to push something, and you can create a force that indeed has the effect of pushing. Then you go there, And I say, okay, but now to push it out, I have to touch the thing. So CIO automatically inserts a cost term in the cost function, which says these two things better get close together if you want to get that magic force, and now the optimizer sees that. So it's actually very simple. Would it work as well as Igor's thing? I only tested in simple cases, and it does work as fast as the Acrobat or whatever. If it scales, well, I don't know. Because Igor had to do some pretty elaborate things. And he comes from computer graphics, which is like the best trajectory optimization ever has been done in computer graphics. And those guys, like they say, for them, physics is just a starting point. And a lot of things happen afterwards.
Okay, so you say we should just go for predicting and picking the best, or at least it's the baseline.
I think it's the best. Look, I hope that Mo actually finishes his thing. I think that he has a lot of good ideas there, and I'd love to try them out. But in the meantime, the rest of us can just try the simple thing. Like, there's no reason not to try the simple thing, only to familiarize yourself with it. And then, okay, then maybe you sit down and write the derivatives if you really.
I think we're in agreement, which is very rare for us. So.
So just to wrap up this, discussion. So you bet. So everybody's betting on something, right? You bet on the simplest thing, right? Just even simpler than reinforcement learning or reinforcement learning, right? Just predicting the user.
You know,
it's more online. I agree that.
I like to think of myself as the casino. I make the blackjack table available. I make you make the bet. I just put out the game.
I have my bet, but you are the people who are in the panel.
I'm going to try different things. I don't know. The honesty.
What's your bet exactly?
I wouldn't make a bet. I don't know.
Great.
There's all these database approaches now. That seems very promising. I don't know. So many things are possible. I think making a prediction or a bet is stupid. I just want to.
You should work on something. You cannot say that.
I can afford to work on everything.
Okay. Great. So, MOU, what's your bet? But how do you think should go forward? Or how? So you are working on your optical, so that's the way to go for you.
Well, optical is a software framework.
Yeah, but it has everything.
What methods work? Okay, so I'm putting everything in it. What methods work? Yeah, I think model-based learning is underutilized and very powerful. Good trajectory optimization, but with continuation and smoothing. Smoothing is going to do a lot. And at the end, when you're done, you can always put some sampling on top of it.
Yeah.
If nothing else, just go and tune some hyperparameters with like base and So not against sampling, question, well, what do you use?
But also, so you are in favor of a smoothing and not going to differentiate to, I don't know, complementarity.
Oh no, I'm differentiating.
No, but you are smoothing it first and then.
I'm smooth. Yeah.
So what do you think, Lynn? So how should we make differentiable simulation?
Well, definitely I'm relatively new to this area. So for me, it's like I'm more focused on like how to deliver this like signals so that you can improve the performance of the organization. That's what I did. For us, it's like definitely gradient is good thing. It's provided us the signals in terms of how to optimize and how to do this. I'm definitely thinking that if there's a differential simulation, there's no reason not to use it. Then the question would become is like how to use it.
And the problem is that it shouldn't be wrong. This is, I think, the most important question. You should find it properly, and it's difficult to find it properly.
So the way to make sure it's not wrong is have finite differences and check against it.
Another thing that I want to say is that the entire idea of using simulation, I think, not in the modern world, is going to depend on the type of work that Lynn showed. Like the sort of real to sim. How do you go from data to simulatable models easily and robustly? I think a lot is going to hinge on that.
We'll get there.
Sorry.
That's the next round.
Sorry.
Don't ruin my plan.
Sorry.
So, okay, great. So what do you think, however? So the question is that basically, I think you are doing interior point method, right, for complementarity?
Yeah.
Basically, we know that most of the theory of optimization, gradient-based optimization that we have really doesn't hold for complementarity systems. right? Do you think that's an issue or no? We should just use gradients and do with gradient optimization.
I don't know. I mean the entire like picture is, I think, too complex. Right? So I cannot say anything. I mean, I suggested some smoothing of complementarity, constraint, but it's not generalizable. And then I think stochastic sampling would be more generalizable in my method.
What do you mean by generalizable?
I mean, so my method only it's only smoothing for the complementarity constraint, but there are many discrete things like for example, Lyot functions and then dynamics, something like that. I mean, I have not smoothed out that kind of discrete function, so it's not generalizable. So, and then I think the geometry is too complex. I think, that we are dealing. So I don't have any concrete answer. Yeah.
Cool. So gradient. Huh? Yeah, exactly. But I will provide the first one. So about gradient, not gradient, is there any question? The first topic was I just took it from the, yes.
If you guys could plot the dimensionality of your problem versus sampling and gradient-based solutions, how would that graph look like? Where will be the intersection?
I'm not sure dimensionality. It's something about the difficulty. The difficulty is really hard to quantify. It's sometimes really surprising what's hard, right? There's that problem that Emma showed the acrobat. It's like a stupid smooth 2D problem, no context, no nothing, but it's shockingly hard. 2 degrees of freedom. And on the other hand,
well, it's shockingly hard for sampling and for RL. Trajectory optimization nails like a couple of Newton interfaces.
yes, but it's still the fact that it needs 2. Right? Why does it need 2 and not 1?
Yeah. Going from linear to non-linear, you would add it with 1.
Maybe I can find something in this discussion. I think gradient sampling and so on. What about parallelization? I think parallelization is a huge thing that comes in if you do optimization, right? You can run the stuff in the GPU, and suddenly we have the parallelization in which gradient methods are not terribly good at, or maybe you have to change the way they work. Typically, they are.
I would disagree with that. So
oh, good. That's great.
So actually, I would say so. If you want derivatives, but you don't have them in your finite difference, you're going to use all your multiple cores for finite difference. Suppose I gave you serial code which computes the gradients. Now, instead of wasting your cores to the finite difference, you can run like 1,000 different trajectory optimizers. Each of them has its own gradient, so you can do like a large number of lead trajectories in parallel. You can always find use for parallel processors if you have them. That doesn't have to be something. Like, I mean, like you want to optimize large number of trajectories from different initial conditions, fine, do it in parallel. Each of them has gradient and has.
Yeah. I want to say, I think the more interesting axis, there's the problem complexity, there's the scaling of the solution, and I think there's a hidden axis here, which is how much work do you need to do? Like the work of the researcher. And that's the axis that's always, it's implicit and it goes into your decision making, but you never show it and you often don't think about it. And I think that's the thing that, and I was advocating to do the easy thing because you get results quickly and it can unblock you and also teach you a lot about what the easy methods can give you. But I'm not disputing the fact that, doing the right thing, which might take more time, might be a much, much better solution, but it's harder to do. But it's a hidden axis, and that's the one that's actually much more difficult. It's very difficult to plot it in the paper.
It kind of correlates with how many authors the paper has. Not to point fingers, but.
Okay, did you get your answer?
Yeah.
Yeah, perfect. Any more questions?
Maybe what about second order derivatives? Because basically one would use any Newton optimization as for the NTC with the leg robots. I guess you're using
Gaussian.
Gaussian.
Yeah, Gaussian. I mean, So if you went to the trouble to compute second order derivatives and your Hessian has negative eigenvalues, now you have to do all kinds of magic. None of them is particularly well motivated. Theoretically. I haven't done much in practice on larger problems, but also if you look at what it takes to compute the second derivatives of the pain. So if you look at these Gauss-Newton friendly costs, like you have a residual and you have a norm. The norm you definitely compute the Hessian analytically. The residual Jacobian is enough, and then you do J, H, K transport. But you end up with second derivatives in a hidden way. So like I was saying, the contact Jacobians, if you want to get the Jacobian of the dynamics, like acceleration with respect to force, for example, you need the derivative of the contact Jacobian with respect to position. What's a contact Jacobian? That's already a derivative, right? So now you're computing the Hessian of the contact distance function already. So they prop up here.
That said, if you do second order derivatives, it's absolute magic. I wish Moritz Deal was here.
He's a student of Moritz.
Ah,
That's why he's asking.
Yeah,
that's
exactly.
why he's asking. So, you know, if you've ever experienced second order convergence, it's like magic. It's like, you know, boom, boom, you're there. But like Amos said, it's painful. So that's yet another. So if there's an axis from me to where Amos sits, then Moritz is one chair over. I have a lot of respect for that, but so.
No, so also the question is if you trade, so you have to do a lot of compute to get those things, even if they're analytical, right? I mean, we're talking about some large tensors. That would reduce the number of iterations of your solver, but we want a large number of cheap iterations, a small number of expensive iterations, not even obvious. I think it depends a lot on how hard it is to compute those.
So I think with your network we have seen as the dimension rises, you want to go only one first order, right?
Yeah, there was that. Oh, I forgot his name now. There's a guy that did a lot of work on getting second order steps. Do you remember his name? He's in DeepMind, which that's what makes it embarrassing. Second order steps in gradient descent. Spent maybe 5 years on that, and he was like, okay, it's actually not.
Maybe try it.
Oh, so should I ask you a question or you're leaving?
Well, ask me a question, I'll answer, and then I'll leave.
I ask you a question and you leave. So basically, I will be quick. So many people here in this conference are talking about deep RL, and deep RL is exactly, policy optimization, right? It's not learning. Learning means that you have data in the real world and you want to use it, right? So how should we use data in the real world?
I mean,
do we need it, or we should, also deep RL people throw it away because they don't use it.
What is deep RL? Like a deep neural network.
No. What I mean is that seems real. You train in simulation, which is policy optimization, right? Then you deploy in the real world, but you don't use real world data, right?
So you're asking about the
Real world data. For instance, system identification should be used.
Of course, for system identification, by definition, you need real world data because the point of system identification is to make the simulation match.
But with contact is difficult, right? So you cannot just separate the system and do system identification. You need to do model-based reinforcement learning in the real world or something like this, right?
You need state estimation and system
identification
together.
Yeah,
to be joined.
That's right.
Through contact. So we need a differentiable.
Especially with contacts, like if you, let's say, this thing is sitting here and you're holding it, you get the estimate like 1 millimeter wrong. Now this thing should be falling.
Yeah.
Why is it not falling? Now maybe you change the gravity in your system ID to explain why it's not falling. It's like the errors in those two are very strongly coupled.
When people are using model-based RL, so they update the model in the RL by system ID.
Yeah, but nobody does it in the real. Yeah, if you want to do it in the real world, right? So if you are talking about real world, which is proper RL, right? Then it means that you should be careful about safety and so on, right? Then safety becomes a problem. So really, for me, at least, it's a question: how should we use the real world data? Should we just ignore it?
I mean, he showed how you can estimate friction online, right?
Yes, and then update your model.
And use MPC with that.
Yes.
Right, that's a good question. But if you're doing RL,
Yeah.
you have a policy that you already learned. How do you update the policy?
Exactly. And normally the gradient space you do it
One
here.
way you do it is the policy has input, which is the state or whatever, and it has some other inputs which basically correspond to system identification.
adaptation.
Right, exactly. You train for all of them with some domain optimization. And then in real time, you kind of figure out what they should be.
Yeah.
For that. That's, I guess.
The domain adaptation.
Yeah, exactly.
Yeah.
The policy, like if you're doing system ID and you have a pre-trained policy, the policy has to be able to work with any system, right? So that means it's an input to the neural network.
I think the two new exciting answers to your question. One is I'm going to answer in
Yeah.
Kelsey's name because I'm not sure if she's with us, and that is take the data and learn a simulator from the data, which I think is very exciting. There's some things that I think it's really useful for, like simulating fabric, things that are really high dimensional, or kind of like summarize, basically doing model reduction. One could also do that with an analytic simulator, right? You could take a simulator that simulates fabric with 10,000 degrees of freedom and distill it down into a much faster to simulate neural network. The other direction is exactly what Lynn is doing, which is take the data and ask, how do I explain this data with my simulator? I think both of these directions are very exciting, and I really look forward to see what people like Kelsey and
You guys
Lynn
do a large language model that's like, or something that looks at the world and writes in the job model file.
Yeah.
They do everything, right? They solve every problem. They should be able to.
Yeah.
It's a large word, it's vision language.
Yeah, we're working on it. I gotta go. Thanks, Majid. Thanks, everyone.
Thank you.
Can we continue or?
I would say we have 5 more minutes.
Yeah.
Let's ask.
So,
let's
question,
audience.
please,
Yeah.
yes.
Question in terms of differential simulators. So basically, they are making instead of hybrid decision, we are making it continuous, like make or break contact. But in certain tasks where we draw the line that we have a high level logic, and then each behavior, those are different behaviors, or what are the cases that everything is a continuous behavior? So where do we find that to bridge that? Oh, now we need to go and have different behaviors, and it's not just a differential. It's a general question, because sometimes maybe it makes more sense to have a behavior that is out of context and behavior that is in context.
I mean, more generally, when you have, like, for example, marked like logic programs or things like options, where like you may have discrete decisions and continuous controls. Continuous one, I think, basically what you want to do is, for a given setting of the discrete variables, you want to be able to solve the continuous problem with gradient-based methods. And how you set the discrete variables, you could sample them, not many of them, or I don't know, do something else. But yeah, I think that's very important. I mean, hierarchical controls are a good idea, and that they should have discrete features.
More questions? Yes.
Yeah, I'm new to differential simulator. I'm just curious about the vision model. Basically, we can have different type of.
Can you speak up?
Yeah. Sorry. I mean, we can have different type of creation models. So, but we can also get a gradient for each of them. But is there a creation model have better, the gradient can better update hyperparameter in the creation model than other types?
So the multiple collision models, the simple ones are geometric primitives like spheres, ellipsoids, whatever. Those are great, but they don't explain everything. Meshes are the most general. It's a pain. There's something called the GJK method, which is the right way to go. This paper that I don't know if you're here, but organizers have a paper which is really nice. It tells you how to differentiate something that doesn't look differentiable, but they managed to pull it off. So that's very promising. There are signed distance fields where depends how they're represented, it may or may not be differential. But yeah, in general, it's a bit like in Joko right now, they're like 3 different collision models. The geometric primitives, there are meshes. There's actually these flex things, that's the 4th one, and there's signed distance field. And if you want to call the whole simulated differentiable, somebody will have to go and differentiate every single one of them by hand. I hope that's not me, but it probably is.
Well, is there a trade-off? Is there a trade-off for better creation model? You want to make it differentiable? Maybe a worse.
I mean, the geometric primitives are the best if fit your needs, like you cannot beat that. If that doesn't work, meshes versus SDFs, I think meshes are the next most useful. SDFs are kind of out there. Yes, there was one more.
So, I want to ask a little bit of a high-level question. We talked about state estimation and system identification. So that we can do real to sim from the real data, but that is actually, I think it's very hard to do. Most methods are from the machine learning side. You mentioned you will not be able to do it with large models, but I think eventually.
I was joking about that.
So yeah, in very like complex systems, very complex environments, we have to roll out. There might still be a some type of error we cannot reduce, even if we have really good learning systems. So in that case, do you think it's necessary to add a bit of magic into the modeling side, or we just need to continue to develop better perceptions?
I think we should do what the Marco Hatter and company have been doing, like put a little neural network that models every actuator because you cannot model it otherwise, and then integrate them. Like if they're well contained, it's like what like you know what I'm talking about, right? So they have their quadrupeds, they have some funny actuators. They model the rigid body dynamics, but the actuators just don't make any sense. So they collect input output data, feed a neural network to it, and then integrate the neural network as part of their whole rigid body simulator, and then gave them some very remarkable improvements. So if you can identify small things where you know where that there is, just feed it. Yeah, that's it.
But if it's not, circular, motors you can take it out and do it, or if you have load dependent terms,
Right. So the motors they could take out.
Yeah,
that's why they could do it.
But if you really need to do it with contact, then
I mean,
you need you can annect. First, you need to generate motion, right? Such that be able to do out such as you
all these contact models, especially the ones we have plenty of parameters. There's a lot of room. I mean, if you look at the stuff that he's doing and she's not here, with this graph network, they're basically those interactions. Actually, there's flexible bodies in Mojoko right now, which can kind of work like that. So there are multiple points that are connected to triangles collide, and there's some passive forces that kind of keep the thing together. You can go and change the spring damper parameters on each edge if you want, and adapt it. And of course, in what they do, that's also. But the more the more parameters you have, the harder it is to identify. I mean, one common observation system idea is you very often. The best fitting model has negative inertia.
But you can do, constraint optimization.
You'll have to start. But if you have too many parameters, you don't even know what's going on.
Yeah, sounds good. I think we can wrap it up. Thank you very much. And
I want to say 2 words very, very quickly.
Sorry, you will do something. Okay. And general
So I want to just say thanks to a few people. So thank you to all the amazing speakers who gave really great presentations. We couldn't have wished for better. And I also want to thank Majid and Fan for stepping in as panel moderators on a very short notice. That has been great. And thank you to all the contributors for nice posters and to all the participants for asking good questions and making lively discussions. And thank you, of course, to all the co-organizers. You have seen most of us today. Of course, there's Michael, who unfortunately couldn't be here, who has been a great help. And so with that, the most important part. So you will be happy to hear that the social is in maybe a rather cool place. So it's in this place called Wintergarten. It's in the center of Munich. You have to take, let me just use this. You have to take the U6 to Gisela Straße, then it's a 10-minute walk. We have a heated tent, but I hope it's not going to be too warm like here. and there will be basically drinks and snacks. And it's in an area of Munich where you have nice restaurants around as well. So I think it's a good starting point if you want to keep going and yeah, have a nice evening. And all of this is the last thing, thanks to NVIDIA, who were generous enough to give us a nice sponsoring money to have this social together. So once again, thank you to everyone, and I hope that we will see you all in some versions of this workshop or another in the future. So, thank you.